Okay, so this video is exclusively going to be about constant acceleration. And honestly, in terms of content, there's nothing here that you haven't learned about in honors physics. That being said, the difficulty this year is going to ramp up a little bit. So I want to show you how to deal with sort of some of those tougher concepts. All right. And in addition, I want to talk about how the equations that we use in honors are different from the ones that you get on the AP physics sheet. Okay, so let's do this. So last year, we learned these guys. We learned that displacement is change in position. All right. Often in the AP book, they don't use final and initial. So this equation, if it was written, on the AP physics equation sheet, would probably say displacement is position minus position at some earlier point. In other words, we're going to replace initial velocity with, we're going to replace initial position with position at time 0. And then final position just becomes position at some later time. Okay. So I am kind of set in my ways because I started teaching AP physics long after I'd started using this notation. So I tend to stick with using initial and final for my notation. But just know that in some textbooks and on your equation sheet, instead of using final and initial, they use this notation here. Okay. Now, if the velocity is constant, right? So that's these guys. If your velocity is constant, the only equation I want to see you using is this. Displacement is velocity times time. Distance equals rate times time. If you go 60 miles an hour for 3 hours, you're going to go 180 miles. Displacement is velocity times time. Okay. If your velocity is constant. All right. If your velocity is not constant, then that's when you need to start worrying about acceleration. And that's when we dig into these equations here. Okay. Now, really quickly, did I do this? Oh, good, I did. Okay, cool. So these are the equations that we learned last year in honors. Okay. So kind of keeping up with what I was just talking about, notationally speaking, this is our equation for acceleration. Okay, assuming your acceleration is constant, final velocity minus initial velocity over time. If that was written, sort of in AP physics lingo, it would be this: acceleration is v minus v naught over t. Okay. In this equation, which we used all the time in regular physics, becomes v equals v naught plus a times t. Okay. And I guess I should be trying to be better about putting these arrowheads on here. Remember, those little arrowheads just indicate, hey, this quantity is a vector. And so we need to sort of use the vector rules, which we'll learn about more as we go through the year. At this point, basically, that just means you got to watch your positives and negatives, right? Okay. Okay, cool. So if I remember correctly, this is the first equation on your AP physics equation sheet. Yep. Oh, right here. Oh, gotcha. And one other thing. So the way these are written is they're saying, all right, let's assume that this is all taking place on one axis. Okay. So for a given axis, the velocity on that axis at some time is equal to the starting velocity on that axis plus the acceleration along that axis times the time. Okay, so that's actually the way that they're written there. So all of these little x's are just indicating for a given dimension, that's how you find the velocity at time t. Okay, so keep in mind, this could be any axis, right? So these could be, if you wanted to, these could be y's or z's. Okay, so that works for any given axis. Okay, just depending on your scenario. Okay, so let me undo those y's that I just put in there. Oops. So this is the first equation on your equation sheet this year. Okay. All right. So let's see. Next equation. What do we got? Oh man. So these red ones here. This one still applies average velocity is equal to the velocity at some time plus the starting velocity divided by 2. Again, all of these equations, I cannot stress this enough. All of these equations here on the screen right now pertain only to constant velocity. So the only time you can use this equation is if it's, I'm sorry, I think I said constant velocity. The only time you can use these equations is if it's constant acceleration. Okay, let me say that more explicitly. These equations are for use only during constant acceleration. Okay, that's the only time we're going to use these equations this year. All right, so following that train of thought, then the second right equation becomes displacement equals 1/2 times v plus v naught times t. Notice these equations, oops, are totally viable, but the stupid AP physics board did not give them to you, okay? So that equation is not on there, all right? I really think that it is worth your while to memorize these equations as they appear here. Because if during your AP test, you're constantly looking at the AP, the list of equations, you're gonna struggle, okay? So you really need to memorize these equations, all right? Now, the blue one and the green one here are on the AP physics sheet, but slightly different notation, okay? So let's talk about this blue one here, all right? So for the blue one, let me write it the way that we do in honors. So displacement is 1/2 AT squared plus VI times T. So here's how we modify this. So we've already learned that displacement is change in position, right? So for us, that's x minus x naught. Okay, final minus initial, x minus x naught equals 1/2 acceleration along the x-axis times t squared plus vi becomes v naught along the x-axis times t. Okay, so hopefully you can see those two equations are basically the same thing. All right. Now, often what we care about is not, well, honestly, most often what we care about is the displacement, which is why I like this equation best. But occasionally we care about the position at a given time. Okay, like not how far has it gone, but where is it? And in that case, we'd be looking not for displacement, but position. So if we rearrange this equation here for x by adding x naught to both sides, then you get this. You get x equals 1/2 acceleration times time squared plus initial velocity times time plus initial position. Okay, and this is actually the equation that's on the AP equation sheet. All right, and we're actually going to use this equation here in a minute. There's one type of problem in specific where this is helpful. The rest of the time, this is your jam. Okay. All right, so I'm going to come back to this one in a minute. And actually, I think on the AP sheet, they actually reverse this so that it's x equals x naught plus initial velocity plus 1/2 AT squared is actually what's on the equation sheet. Okay. All right, so that is where this equation comes from. All right, it's the same as the blue equation on your honors physics sheet. All right, finally, this last one down here, this guy is actually the green equation. Okay, so let me show you that now. All right, so this guy, whoa, this guy from a AP perspective is going to look like this. So the original equation is 2a delta x equals vf squared minus vi squared. So that's going to become 2 times the acceleration in the x dimension times, remember, displacement is x minus x naught equals vf squared just becomes v squared in the x direction minus v naught, that's like your initial in the x direction squared. Cool. So that's that. And then what do we need to solve it for? I forget now, sorry. We got to solve it for, okay. So then they just solve it for vx squared by adding v naught x squared to both sides. So you get into acceleration in the x direction, change in x position, plus initial velocity in the x direction squared equals vx squared. All right, and so there's your last equation on that AP physics sheet. All right, so honestly, when I do my problem solving this year, I'm pretty much going to stick to these guys. All right, really, I think the only time that I ever use sort of the AP physics version of the equations is this one if you're looking for position. Okay, so those are the equations. If I have not made this clear, you really need to memorize these equations, you guys. All right, people, because they're going to be coming up all year. Okay, very often these equations, both here and here, are referred to as kinematics equations. Okay, so if you ever hear me use the word kinematics, I'm talking about these equations here. Kinematics equations. All right, cool. So let's apply some of this. All right, let's do an example. All right, and I've got two different examples for you here. I'm not going to review honors stuff. You know, honors stuff would be write out your givens, pick an equation, solve for the missing thing. Okay, hopefully you know how to do that. All right. So what does an AP style problem look like? All right, well, so here we go. So here we've got this helium balloon. It says it's released from the bottom of a cliff and it's going to float up from the ground at a constant speed of 6.7 meters a second. At the same instant, a tennis ball is thrown down from the top of the 49-meter cliff at 8 meters a second. And the question wants us to say at what time they cross paths. Okay, so let's get a drawing of this. So here's our cliff. All right, and we've got two objects that are sort of in motion. So why don't we do the balloon using red. There we go. So here's our balloon. We'll do that using red. So here's the balloon. Why did that not go red? That's annoying. There we go. Here's our balloon. So the balloon is going to move up. Stupid smartboard. The balloon is going to move up at a velocity of, what did we say? 6.7 meters per second. That's the velocity of the balloon. Oh my gosh, it's so frustrating. And I'm going to make a note that that is, in fact, constant. Okay, so there's my balloon. All right, meanwhile, we've also got a tennis ball. All right, and the problem tells us that the tennis ball is thrown down. All right, so I'm going to do all my tennis ball work using this green color. If you're colorblind, I should not have, well, I've already done it. So I'm sorry if you have a tough time with green and red. All right, so here's my tennis ball. It is being thrown down with an initial velocity of -8 meters a second. Okay, and what we want to do is we want to figure out when they cross paths. So this is a scenario where we care about position, because the idea is if you picture the two objects moving towards one another, at the instant when they cross paths, they're going to have the same position, right? They're going to be at the same vertical position. All right, and that's what we care about, is we want to know at what time does the tennis ball and the balloon have the same vertical position. So let's write out what we know. So for the balloon, here's what we know. I know that the velocity is, as I said a minute ago, 6.7 meters a second. I know the acceleration is 0. Now, to talk about position, we need to decide on an origin. All right, so what we should be picturing is a number line that runs vertically along my cliff here. And let's call the bottom of the cliff a position of 0, which means since the cliff is 49 meters tall, that means the position at the top of the cliff is going to be 49 meters. All right, now there's nothing magic about this. I could have, if I had wanted to, made the top of the cliff a position of 0 and made the bottom -49 meters. Okay. But you need to, choose some sort of origin. All right. So with that in mind, then let's continue with what we know about the balloon. We know that the balloon has an initial position of 0. Or I guess using AP physics lingo, x0 is 0, right? The starting position of the balloon is 0. Okay. Now, for the tennis ball, what do we know? Well, for the tennis ball, we've got an initial velocity of -8 meters a second. We've got an acceleration of -9.8 meters per second squared. And we've got a starting position up here of 49 meters. All right. Now, honestly, for this problem, what I'm about to say is not that big of a deal. But moving forward, it's something that I often see students get messed up on. All right. I have a contradiction here. And it's nitpicky. This is super nitpicky, but again, it will cause you problems later on in the year if you're not careful. Right now, I've got acceleration being two different things, right? I've got acceleration being 0, and I've also got acceleration being -9.8. That can't possibly be true. Acceleration can't be 0 and -9.8, all right? Please don't use the same letter to represent two different things, okay? Everything that I have written here in red pertains to the balloon. So that acceleration isn't acceleration, it's acceleration, oops, it's acceleration of the balloon. So I'm going to go ahead and put a B on each of these variables to indicate that they're for the balloon. And I'm going to go over to the tennis ball stuff and I'm going to put a T on each of those so that I know that they pertain to the tennis ball. Okay, that way, it also helps me understand what these two different starting positions are, right? This x0 B is the starting position of the balloon, and the x0 T is the 49 meters for the tennis ball, okay? Also, I guess I should comment on this. I just said x0. That's how you say this, initial position. Usually people say x0. Not means 0 in, I don't know, British or something. And yeah, okay, cool. So let's write out an expression. So here's what I'm trying to figure out. I'm trying to figure out there's going to be some time when the position of the balloon equals the position of the tennis ball. And I want to figure out when that happens. Okay. So we need to write out an expression for both positions. Okay. So let's do this. Boom, boom. So for the balloon, the position of the balloon as a function of time is, well, it's velocity times time, right? The velocity of the balloon is constant. So it's going to go 6.7 meters per second every second. And I'm just going to note it started at a position of 0. Okay. So if you're keeping score, what I really just did there is I used this equation. No, I didn't. I used this equation, but I solved for final position, right? X minus x naught equals VT. X equals VT plus x naught, right? So that's what I just did there, because the velocity of the balloon is constant. Okay, so that's the position of the balloon at time t. Let's write it in simpler notation. The position of the balloon is 6.7 t. All right. Now, meanwhile, the tennis ball has acceleration, right? And so we learned that the position of something that's accelerating is this guy, right? So that's the equation I'm going to use for the tennis ball. So the position of the tennis ball is, so the equation is x naught plus v naught in the x direction times t plus 1/2 acceleration in the x direction times t squared. Let's plug in our numbers. Position of the, no, should use a capital T for tennis ball, capital T for tennis ball. All right, equals, let's see, starting position is 49 plus initial velocity is -8 t plus 1/2 times -9.8 t squared. Position of the tennis ball is 49 minus 8t minus 4.9 t squared. Okay, so what I've got now is two expressions. I've got an expression that tells me where the balloon is at time t, and I've got another expression that tells me where the tennis ball is at time t. And I want to find the time at which those two things are equal. Okay, so I'm going to set the red equation equal to the green equation. So I'm going to have this equals this, right? So 6.7t equals 49 minus 8t minus 4.9t squared. And now I got to solve this mess, right? So let's move everything over to the left and set it equal to 0. So I'm going to add 4.9t squared to both sides. I'm going to add 8t to both sides. So that gives me 14.7t. Then I'm going to subtract 49. So now we got to solve this. And so there's a couple of ways you can do it. In most instances, I would say, well, just use the quadratic formula or plug it into your calculator and solve it. That's totally a thing you should know how to do, is how to solve a quadratic formula using your calculator relatively quickly, and ideally without using the quadratic formula. So if you don't know a way to do that, remind me in class and I can show you some tricks to do that. Or more importantly, there's somebody in class who can show you some tricks. All right. Now, because I wrote this problem, I cheated. All of these things are divisible by 4.9, which you wouldn't notice, but they are. So I'm going to factor out a 4.9. So this becomes 4.9 times t squared plus 3 minus, plus 3t minus 10 equals 0. And then this factors. So you get 4.9 times, let's see, this is t plus 5 t minus 2. So either t is 5, sorry, negative 5 or 2. Time can't be negative, so t must be 2 seconds. So that's the time at which they pass. And so then to find the position, just plug t equals 2 into this, or t equals 2 into this. And in either case, you get that your position is, what, 6.7 times 2, 13.4 meters up from the bottom of the cliff is where they cross paths. Okay. All right. There is a lot going on here. All right. This is a very kind of a classic physics problem, right? We've got two moving objects. When do they meet? So the trick for this is you write an expression for the position of each one and set those two positions equal to one another. Okay. As you are doing that, you need to consider, is the velocity constant or not constant? If it's constant, it's just velocity times time. If it's not constant, then you got to do the 1/2 at squared equation. All right. So there we go. All right. Now, on to other things. Oh, you know, I guess I should comment also. Let's graph. Do we want to mess with this? You know what? Let's graph these. Do I want to graph them? I wasn't planning on it. Yeah, let's do it. Whatever. Let's do it. I got a minute. Suppose I asked you to graph these. So let's make a position time graph. Position, no, position in meters, time in seconds, right? So for the balloon, it's floating up at a straight velocity, right? So here's my balloon. So red is the balloon. Because the velocity is constant, it's going to be a straight line, right? So this line here has a slope of 6.7. Okay. Now, the tennis ball is being thrown down, right? So it starts at a position of 49. The slope is going to start negative, but as it goes down, it's going to get steeper and steeper, right? Notice, remember, the steeper a position time graph is, the faster it's going, okay? And what point do we know? Well, we know that at the end of, what did we decide, 2 seconds, they cross at a position of 13.4 meters. Okay, so there's your graph. And then ideally, I guess you should probably figure out this time here, you know, the time at which the tennis ball hits the ground. Okay. All right, so sometimes things are a little bit more abstract. So here we go. Roy is driving his car and he slams on the brakes and stops in some distance. The next day, he's driving 4 times as fast and he again slams on the brakes, stopping with the same acceleration. How many times farther does he travel before stopping? And then what's the ratio between the new stopping time and the old stopping time? Whoa. All right. What's even going on here? There aren't any numbers. So this is a really abstract problem, and these come up on the AP exam all the time. And this now being, I guess, I don't know, my 6th year teaching AP physics, I've realized this is a thing that AP physics students struggle with. And I think I'm pretty happy with, this is a way to consistently solve these problems. It is not always the easiest way, but I often find that some students don't sort of just have like a natural intuition for this. And they need like a cookie cutter way of doing it. And this is a way of doing it. All right. So here's what we're going to do. We're comparing 2 things. So in the first sentence, it tells us he's driving and he slams on his brakes and stops. And then the next day he slams on his brakes again. So we're comparing the 2 days, right? And in question number 1, what we're trying to find is how many times farther he travels the second day. So if I consider my stopping distance, delta x, I'm looking for the stopping distance on day 2 divided by the stopping distance on day 1, right? In other words, if the stopping distance on the second day is twice as big, then this ratio here will be 2, right? That's what I'm trying to figure out. So the crux of this is there are 2 days. All right, so let's do everything for the first day. We'll call this day 1. And we'll do everything for the second day in, I'm going to reuse blue. And you're just going to have to deal with it. So the next day, we're going to call that day 2. All right. So what do we know about the 2 days? Well, the first day he's driving, he slams on the brakes and he stops in some distance. The next day he's driving 4 times as fast and he again slams on the brakes and stops. So here we go. So on day 1, he's driving at some, oh shoot. On day 1, so day 1, his initial velocity is something. And then on day 1, he's going to slam on the brakes, so his final velocity is going to be 0. And his acceleration on day 1 is something. All right. And I'm trying to find out information about, the stopping distance on day 1. So, oops. So stopping distance on day 1, let's call that D. No, I don't even need to do that. That's what we're trying to find. Let's just call it question mark. I'm sorry. Totally have a system here. I'm not using it. All right, this is delta X. I don't know why that black is there. All right, now on day 2, what do we know? So on day 2, it tells us he's driving 4 times as fast. So that means the velocity on day 2 initially is 4v. Please notice, every variable has its own name here. In the red column, I put a 1 subscript on everything to indicate that that's day 1. And over here on day 2, I put all these 2s on here, right? And so the velocity on day 2 is 4 times what it was on day 1. If you really wanted to, you could do this and not introduce that v variable, okay? But I'm going to stick with that. So the initial velocity on day 1 is v. On day 2, it's 4 times as fast. Now, on day 2, we're still stopping. It tells us same acceleration. So the acceleration on day 2 is also a, and again, I'm interested in my stopping distance. Okay. This process is huge. Okay. These numbers are what are going to allow us to solve this problem. And it's weird because there sort of aren't any numbers, but I'm still writing out my givens. Notice the problem doesn't, until question number 2, the problem doesn't say anything about the stopping time. So time is not one of my variables. The only variables referenced are starting velocity, VI, he's stopping, VF, acceleration, and stopping distance. That's my 4 variables. Okay. Now, my goal is, what I want to find is the ratio between the stopping distance on day 2 to the stopping distance on day 1. That's what I want to find. Okay, so here's what we're going to do. We're going to look at our equation list, and we're going to come up with an equation that uses these 4 variables. All right, and so the one that jumps to my mind is this guy. 2a delta x equals vf squared minus vi squared, right? From honors. Again, I really think the honors equations are better than those AP ones. So even though you get the equations on the AP sheet, they're formatted weirdly. All right, so I want to solve this equation for delta x because that's what I'm looking for. So this becomes delta x equals vf squared minus vi squared all over 2a. Okay, so now what I'm going to do is do this. Again, what I'm trying to find is the ratio between the displacement on day 2 over the displacement on day 1. So on day 2, I'm going to use this equation. Let's see, on day 2, VF is 0. So I'm going to have 0 squared minus, let's see, VI is 4V. So I'm going to do 4V squared all over 2a over the same thing on day 1. Oh shoot, that was supposed to be in red, wasn't it? So now I'm going to take all of this stuff and plug it into this equation. So on day 1, I have 0 squared minus v squared all over 2a, right? And now it's algebra. So I don't know how you want to algebra this. I'm dividing fractions. So let's multiply by the reciprocal. So the blue becomes 0 minus, let's see, 4v squared is actually 16 times v squared. 0 goes away all over 2a. So that's the blue part simplified. Divided by the red. So I'm going to multiply by the reciprocal. So times, I'm going to have 2a on the top, and on the bottom, 0 minus v squared. And then simplify. So let's see, the 2a's cancel, the negatives cancel, the v squareds cancel, and you get 16. That means he's going to stop in 16 times the distance on day 2. Okay. All right. And then question number 2 asks about the ratio between the stopping times. Oh, well, so for question number 2, let's do that using, I don't know, purple. For question number 2, I want the time on day 2 divided by the time on day 1. So again, using my given information, time is VF minus VI over A, right? So on day 2, we're going to have VF minus VI over A. And on day 1, I'm going to have 0 minus V over A. And you can see everything here cancels except the 4. So we discover that that ratio is just 4. It's going to take him 4 times as much time to stop on day 2 because he was going 4 times as fast. Okay. Now, this is definitely not the only way to do this. I don't even think it's the easiest way to do it, but it will always work. Okay. Now, as you start to do more of these, and there's a bunch of them on your first couple homework assignments, hopefully you'll start to develop an intuition for it, and you'll start to see how you can just kind of go straight from this equation to the answer, or from this equation to the answer. But it takes some practice. And in my experience, students walking in the door at the start of the year in AP Physics don't all have that. So it'll take you some practice. And if you don't get there, this will always work. All right. Okay, this video was longer than I hoped it would be. Most of them are. There you go. Have a good day. I gotta stop recording. Boom. Stop recording.